Okay, hi class. Today we're looking at section 4 of chapter 7 as we continue with our independent study. This section takes a little bit of a turn. We've looked at simple interest and compound interest, and now we're looking at the effect of making compounding interest calculations on multiple payments or multiple deposits. Could be on a loan, or it could be for an investment purpose such as saving money in the future. But for an annuity, we usually describe annuities based on different types. The simplest type, called an ordinary simple annuity, is when we're making payments at the end of each compounding period. And that means that whenever interest is compounded, another deposit will be put into the account or made on the loan. And when we see the amount of an annuity, it's different than the amount of a single compound interest investment. The future value of an annuity is simply the sum of the regular deposits plus all the interest that each one has earned individually. When we look at how to tabulate the growth of an annuity, we need a scenario to look at and a couple of simple rules to follow. So let's use the investigation in our textbook, which is found on page 440. 444 in your textbook, you have this situation. Colin awarded $500 per year as long as he maintains a certain average. This would be a sort of a scholarship program that he's on, and he's deciding that he's going to take that and consider it almost as income rather than putting it towards his education. He's going to use it as an investment for future financial need. Now, the interest rate is small and it's only compounded annually. So the frequency is once per year. And what we want to do here is track the progress of his annuity when he makes his 4 $500 deposits. When we do this, what we're going to do is we're going to put a given deposit in at the end of the year. We're going to calculate interest on that, and then we're going to carry that interest plus principal over as the starting balance for the next year. So here we are. When we do that, we're calculating a 1-year compound amount, because that $500 deposit is only earning 1 year of interest before it gets rolled into the next year's opening balance. We'll show the calculation for interest earned as before, using amount subtract principal, and we'll also show the cumulative progress of the annuity by adding the deposit to the amount. That would be once the next deposit is made. So let's see how this plays out. With this table, we have to make sure the interest is calculated before the next deposit is made. So for our year 1, we have the following figures. Now, since the starting balance for that year was 0, he had no money in the account until he made that deposit at the end of the first year. No interest is earned, so the 1-year compound amount is 0, and the only value that's contributing to the ending balance would be that single deposit. So going into the second year, we now have a $500 opening balance, and we'll calculate interest on that as follows. So starting balance for year 2 is $500. Now at the end of that second year, another $500 deposit is going to be made. But because that money was there, the borrower of the money is going to pay interest on it at a rate of 4%. So for that entire year, we'll have one compounding amount based on principal times 1 plus interest rate to the exponent n, where n is the number of compounding periods. Well, this $500 is going to be earning interest for 1 compounding period, so we're going to calculate its 1-year compound amount as follows. The interest to earn we'll calculate after, and then we'll sum them together to get the ending balance. So at a growth rate of 4%, $520 is obtained from a $500 principal, which means that $20 interest was earned. The $500 deposit is more of your money going into the account, which now gets rolled in together, combined with the 1-year compound amount. So we'll have our $500 deposit plus the $520 from that second year, which gives us a year ending balance of $1,020, by the time the second year has ended. So he's put in $1,000 of his own money, earned $20 of interest. So opening balance for year 3 now becomes 1,020. At the end of that year, another $500 deposit is made. We'll calculate the interest on the 1,020 opening balance for 1 year period of time, and then we'll calculate the ending balance. And we'll repeat this until we've gone to the end of the 5 years. Now, I misspoke earlier. It's only a 4-year term for the investment. So I've carried over the balance to the 3rd year, and another deposit is made there, earning us at the end of the 3rd year $1,560.80. That gets carried over. 1 more year of compounding is applied, and a final deposit of $500 is made. That's his 4th $500 scholarship value, which gives us a grand total of $21,23. So at the end of 4 years, he's put in 4 $500 amounts. So the total principal is really his own money of $2,000, and the final amount here is the $21,23. That would be principal plus interest. So we could see that the total interest earned would just simply be the sum of these 3 values here, which would be the $123.23. So this is an annuity. It's very similar to calculating compound interest over time, except in this case, we carry over the balance and we add a new deposit at the end of that year. But the crucial thing to remember is that for an ordinary simple annuity, the deposit is made at the end of the year, and that deposit is only added onto the interest earned for that compounding period after, because of course you don't earn interest on money that you've just deposited. It's money that's been in the account for that entire compounding period. So with an annuity, there's many possibilities that we can consider as far as applications or uses of an annuity. We've considered here, this would be sort of a savings plan of sorts. So savings plan, we can have long-term investments if we're saving for retirement. In this case, in the short term, it might be just saving for a little bit of tuition later on. Long-term investment goals, example, maybe retirement, or we could have education, depending on when the annuity is started. Long-term could be parents putting the money in at the birth of their child and investing it for maybe up to 20 years before their son or daughter goes to school. We also have annuity applications in situations where money has been borrowed. So again, loans, loan repayment, where the regular deposits are actually money going from you to the lender. You borrowed from them through either a purchase of a vehicle or purchase of some item, or possibly you just borrowed money. And there certainly could be other applications that we could think of whenever either money borrowed or money invested is considered. So for this 4th type, you might just want to consider one of your own financial goals right here that would involve making regular deposits. And you don't have to make deposits of much size to actually benefit from an annuity. If you invest for a long period of time, compound interest plays out in your favor. All right, the next thing we're going to have a look at is how we can use knowledge of geometric sequences to determine the formula for the total amount of all of these deposits plus the interest. Previously, when we tabulated it, it was a little tedious. We had to take it 1 year at a time, and we had to roll over the ending balance, and we had to sum all of those. At the end, we have the interest earned, but if we're really just concerned or wondering about the future value, total amount of the annuity, we can use a timeline also. And what the timeline allows us to do is it breaks these deposits down into separate portions, each of which have a different length of time. So the compounding period for the first deposit is actually 3 years. It would be compounded 3 times between that first deposit and the end of the 4 years. The second deposit would have been compounded for only 2 years in third and the fourth years, and the third deposit would have been compounded only for 1 year in that last year, and finally the last deposit would not be compounded at all. The total of these 4 amounts would give us the amount of the annuity, and let's compare that to the previous figure, which we have tabulated as 21, 23, 23. So we know that the future value of this annuity is $2,123.23. Now, when we look at these 4 amounts, we get $562.43 for the first deposit compounded for 3 years, $540.80 for that second deposit compounded for 2 years, $520 for the third deposit compounded for 1 year, and the final deposit not compounded at all. The sum of those, of course, not coincidentally, totals to the exact same figure here. It's 4 deposits of $500 is $2,000, and the interest earned is exactly $123.23. Now, if we look at those a little closer, let's look at our table. We saw 520 with a $20 interest earned early on. We saw $540.80 with $40.80 earned, and we also saw a $562.43 amount for the later investments. So just the order is reversed here. So just take note of those numbers: 520, 540.8, 562.43. Okay, they all appear, at least the interest portion appears in all of them, except in the opposite order. So those amounts are being accounted for, which satisfies maybe a begging question. Well, would this give the same results if we don't carry over the balance? If we just track them as separate deposits, one deposit for 3 years, another deposit for 2, one deposit for 1 year, and a final deposit for no years, will that still give the same value? Well, it will. So taken individually or taken collectively, where we carry over the total balance, we still get the same future value for the annuity. The advantage with this method is what we're able to do, by showing these individual amounts as a sequence, 500, 500, and 20, or I'm going to show it as 500 times 1.04, 540.8, or 500 times 1.04 squared, and finally the 562.43, which is 500 times 1.04 cubed. Shown like this, it exactly mirrors a geometric sequence where A is 500, and we have a common ratio, which is our multiplier of 1.04. And we know how to sum the terms in a geometric series, don't we? In this case, the sum of a geometric series, according to the formula that we've seen previously, is A, bracket r to the n, subtract 1, all over r, subtract 1. In this case, we could load in our first term, which is 500. R would be the common ratio of 1.04. There are 4 terms here, and it's 4. Common ratio subtract 1 would just simply give us our annual interest rate. And if we pause and calculate that, the sum of 4 terms here for this annuity can be also shown to yield the same value, 21, 23, 23. And there the calculation is in fact yielding the exact same value. So we have 3 now different ways we can get the amount of the annuity. We can tabulate it sort of the accounting style way, looking at balances and interest. We can use a timeline diagram and add up the individual deposits with their different compounding periods, or we can treat this as a geometric series, which is a sequence whose terms are summed using the amount of the deposit as our first term, and using the growth rate, which is 1 plus the term interest rate, as our common ratio. Now, specifically, this approach with the sum of a geometric series yielded the same result, but generally, will it? Let's have a look. Okay, let's look at a general timeline where we have years, or this could be compounding periods, all the way from time 0 to the end of n compounding periods. When we make deposits at the end of the term, we'll have the final deposit made at the end of the investment. The previous one gets compounded for one compounding period. Could be a year, could be a month, could be a week. The one before that would have been compounded for 2 compounding periods, and so on. When you get all the way back to the very beginning of the investment, the very first deposit has been compounded for n subtract 1 compounding periods. If, for example, there were 10 compounding periods, and then that first deposit, which we're calling R in value, would have been compounded for 9 compounding periods. N subtract 1 fits there. The next one would have been compounded for 8, n subtract 2. The one that followed would have been compounded for 7, n subtract 3, and so on. When we look at the collection of all these, the total of all these, including the very last deposit, would be the amount of our annuity, which of course is a geometric series with first term R and growing according to the pattern that we had already seen. Common ratio is 1 plus I, and the number of terms is n, where the very last term is of form a r to the n subtract 1, and you'll very much be right if you recognize this as fitting the general term of a geometric sequence. So we have n terms. A is r, and that would be our regular deposit or payment. It's either an investment payment or it's a loan repayment. And the common ratio R is 1 plus I. And so when we put that all together with what we know about the sum of n terms, we get R in place of the first term. We get, careful here, patterning it after a r to the n, common ratio to the n, subtract 1, all over r, subtract 1, and of course the numerator won't simplify any further than that, and I'll use a square bracket to clean that up a little bit. However, the denominator becomes just simply I. The sum of n terms we'll now call A, or in some cases future value is more appropriate, and we clearly have to know that whenever we use this formula, we're not talking about a single compound investment, we're talking about an annuity based on the complexity of the formula. We should remember that this is not going to give us a compound interest amount of one deposit, but many, and this is our formula that we want to start using now. This is the amount of an ordinary simple annuity. Over on the next slide here, I have this shown, and you can copy out the specifics, but they've been mentioned already. A is the amount in dollars, R is the regular payment in dollars, I is the interest rate per compounding period, or what we call the term interest rate, as a decimal, N is the number of compounding periods, and of course we only use this formula under those conditions. Payment interval is the same as the compounding period, and payment must be made at the end of each compounding period. When we use the TVM solver, we'll have an opportunity to indicate when the payment is made, whether it's made at the beginning or the end, and we'll always choose the end. The first payment is also made at the end of that first compounding period. When we use this formula, of course, there's a lot of operations involved. So if I was to show a simple arrow diagram starting with the term interest rate, what would we be doing to that? Well, working from the inside, brackets out, first thing we have to do is add 1. After that, we're going to take that result, raise it to the exponent n. Then we're going to subtract 1. That completes the square brackets. Finally, we're going to multiply by r and divide by I again. And the result will be the future value. Take note that this arrow diagram just simply shows the progression of operations. It's not possible to use this arrow diagram to solve for I, because the very first thing we have to do in the reversal of this is multiply by I. Well, if we don't have I, we can't use it. But we can certainly say if we reversed all these steps, we would be applying them in an attempt to solve for something which we already knew if in fact we were able to multiply that by that. So anyway, this is more useful in the forward direction, where we're trying to from the interest for the compounding period convert to the final value on the left side.